on this slide, we did the resonance structures, double-headed arrows. And then we took those resonance structures and then made a hybrid. The hybrid was just a kind of an average of the two. The resonance structures, these are two equal structures. It's just different ways of arranging the electrons. We never move the atoms. We just leave atoms in place and then look at ways of arranging the electrons. All right, then, like I said last time, this should have been broken up into two slides. Isomers and this hybrid stuff, this is not related. Isomers, this is another topic. So it's a new topic, isomers. I didn't talk about that just yet, but when you're drawing Lewis structures, sometimes you come up with different structures for the same compound. It seems like the same compound, or the same formula, I should say. So for example, C2H6O. C2H6O, there are two Lewis structures that you can come up with. There are different ways we can put this together. You know, one way of putting this together is like carbon. You know, carbon has 4 valence electrons. If it has 4 valence electrons, in order to get an octet, it's going to want 4 more electrons. Well, how can it get 4 more electrons? One way it could get 4 more electrons is by forming 4 bonds. And so carbon likes to form 4 bonds. Now the bonds it can form are, you know, it can form 4 single bonds, or 2 double bonds, or 1 double and 2 singles, or 1 triple and a single. And so there's some variety in how it can complete its octet, but overall it'd like to form a net 4 bonds. Hydrogen only needs to form 1 bond. Oxygen would like to form 2 bonds. The 2 bonds could be 2 single bonds or 1 double bond. But those aren't the only way. You know, there are other ways they can gain electrons, like form an ion, etc. Forms like carbide. The carbide ion has an octet with 4 extra electrons, because carbide is C4 minus. That would be carbide. So it took those electrons from something that must have a very low ionization energy, because carbon is not a very strong oxidizer. And so it needs to react with something that holds on to electrons very loosely. But sometimes we can kind of get an idea of what the structure is going to look like based on this. So there are different ways we can put these kind of puzzle pieces together to generate these structures, or we can come up with different skeletons, etc. But anyway, the two isomers for this are quite different. And so there are different ways we can write the formulas. So this is what we call condensed structural formula, or condensed Lewis kind of formula. One of these structures looks like this, where, okay, we have a carbon here, it's bonded to 3 hydrogens, and this carbon's bonded to 2 hydrogens, and then we have an oxygen. This oxygen is going to be bridging, that is, it's going to link the carbon and the hydrogen like that. Do you recognize this molecule? This is C2H6O, and the name? Or CH3CH2OH, or C2H5OH. C2H5OH is often used for this as well. But all these refer to this molecule. This molecule is ethanol, or ethyl alcohol. The other isomer for this is CH3OCH3. It has the same formula, but the structure is quite a bit different. In this case, we have a CH3 over here, and this O is linking the two CH3 groups like this. So if we condense this Lewis structure into a formula, this is it. So we call this a condensed structural formula because this tells us the structure. The same here. And so these two structural formulas are different, but the molecular formula for both is the same. They're both C2H6O. So we lose some of that structural information. And we have one carbon we call a meth. And so these CH3 groups are called methyl groups. So this is called a dimethyl ether. If we have 2 carbons, like a CH3CH2, a CH3CH2 group is called an ethyl group. And so sometimes this is called ethyl alcohol, you know, because we have this ethyl group, two carbons attached to an alcohol right here. So ethyl alcohol. Ethyl alcohol and ethanol are the same thing. Just two different ways of saying it. The same can be said for something like methanol. Methanol would be a one carbon alcohol. Methanol or methyl alcohol. But anyway, these are two isomers, and these two are totally different in terms of properties, both physical and chemical. But they have the same molecular formula. They have the same composition, exact same composition. And so that's what isomers are. Isomers are two compounds having the same molecular formula but different structural formulas and different structural. Different structure means different physical and chemical properties. This should be on a slide by itself, but they put it on the same slide here. Again, probably just to reduce the number of slides, but it's really it's a separate topic. This has nothing to do with resonance structures and isomers at all. In fact, there are no resonance forms or isomers for ethanol or dimethyl ether. Sometimes there is, sometimes there isn't. It just depends on the formula itself and the structure itself. And so I don't understand the organization of this. So I would have changed it, but it's okay. We're just going to go with the book. All right, when we did, yeah, this tells us the structure, but you know, this structure is just flattened 2D structure. When we do Lewis structures, we don't really do the structure. If you really want to do the structure, you have to look at it three-dimensionally, you know, how the atoms are bonded in 3 dimensions. When I look at this, it looks like the HCH angle. Do you see the HCH angle? What would you say? I would say that's a 90-degree angle. But in reality, it's not a 90-degree angle. In reality, this is a 109.5-degree angle. And so the Lewis structures need not adhere to the actual 3-dimensional structure. Lewis structures, we just draw with total disregard of the actual structure. We just kind of place them all together and make it neat in some way. So we have some Lewis structure. But based on the Lewis structure, we can get an idea. In fact, we can predict, you know, what the 3-dimensional shape of this is going to be. And predicting what the 3-dimensional shape of this is going to be and the 3-dimensional shape of this is done by Vesper. People pronounce this Vesper. V-S-E-P-R. Vesper stands for valence shell electron pair repulsion theory. In other words, what we're just looking at is we're just looking at the Lewis structures and trying to extract, you know, what the 3D structure is based on the Lewis structure. Lewis structures come from the quantum mechanics. And so this is kind of like applying quantum mechanics in a non-rigorous way. It's not totally rigorous. If we applied quantum mechanics in a rigorous way, it spits out the structure. In order to determine or understand the structure, we need to know two things. We need to know something called the bond distance. The bond distance is the distance between the center of the atoms. And so if we know the distance between the centers of all the atoms, that's the bond distance. And then the other thing we need to know are the bond angles. We need to know what the angle is. So we need to know the distance and the angle. We know the distance and the angle. We have the complete 3-dimensional structure of the molecules. And so anyway, this is a non-rigorous approach. And this non-rigorous approach, what we're going to do is we're going to do this. The electron pairs repel each other. Well, this is pair is the incorrect. Pair. That's not really the right word. A lot of people, what they'll do is they'll substitute. Instead of using pair here, they'll call it a group, like an electron group, because not everything's a pair, and so this can be misleading. But anyway, what we're doing is we should call this electron shell electron group repulsion theory. Electron group, so it'd be Vesper rather than Vesper. That might be better. Because what happens is this, and I'm going to skip that. Groups of electrons are negatively charged. Since groups of electrons are negatively charged, they kind of repel each other. So I can have a group of electrons here. This looks like a single bond. A single bond is a pair of electrons. So I might have a pair of electrons here, a pair of electrons here. They want to get as far apart as possible. In order to maximize the distance from each other, they'll adopt an angle, like this here. In other words, to maximize the distance, they're going to be on opposite sides of the atom. So this pair and this pair will be on opposite sides. But does it have to be a pair? It doesn't have to be a pair. For example, if you have a double bond, that's two pairs. And so you might put a double bond here, and on the opposite side put a single bond. So that would be two groups. Or a triple bond here and a single bond there. A triple bond, we don't call that, well, we don't call it three separate pairs. We just call it one group of electrons. Well, anyway, just visualize these as groups. And so if I have two groups of electrons, they want to get as far apart from each other, that would be 180 degrees apart from each other. That would be as far as apart as you can get. Now, if I put a third group of electrons in there, in order to maximize the distance between three groups, they'll have to adopt this geometry. You know what we call this geometry here? This geometry is called trigonal because it's triangular, planar. It's planar because it's flat in the plane. So, trigonal planar. In trigonal planar, if you want to maximize the angle here, it's 120. If I put a fourth group in here, they'll push these three away. So if I put a fourth group in here, it adopts this geometry. Do you know what this geometry is called? If I have four groups of electrons, this one is called, this one's tricky, this one's called tetrahedral. And a tetrahedral is based on a tetrahedron. Tetrahedron is a four-sided polygon. So what I can do is this. I can connect all the points here with a line. So let's connect these points here. That makes a face of a polygon here. And then there's another face here, another face here, and one face down here. There's four faces on this polygon. A four-face polygon is a tetrahedron. What does a tetrahedron look like? I'll show you what a tetrahedron looks like. It's a four-sided polygon. Tetrahedron. So, as I said, it depends on the groups. And so, let's take a look at the types and varieties of groups of electrons. One group of electrons, we'll put an atom A here, would be a single bond. A single bond here. Another group would be a double bond. Now, double bond, can I split that into two singles? Or how about this? You know a single bond, how many electrons does a single bond consist of? A single bond consists of two electrons. Can I just split those into one and one? One electron here, one electron there on the opposite side? No, because it's a bond. It goes together, so that's considered one group. So this is one group. A double bond, no, we don't split double bonds into two singles. And so this is considered one group, except it has twice as much electron density. When it has twice as much electron density, this is what happens. With a single bond group, I have two electrons, and the two electrons are in a tug of war between B and A. So B is trying to pull on the electrons, A is trying to pull on the electrons. So it's spread out. If I have a double bond here, there's twice as many electrons in there. If we have twice as many electrons, one thing is that's twice as much negative charge. If there's twice as much negative charge, it's going to pull the atoms closer to one another. And so a double bond is shorter. Not only is it shorter, it's stronger. Is it twice as strong and twice as short? No, it's not, because all the electrons aren't concentrated in one spot between this center of the atoms. It's kind of spread out. So it's shorter though, for sure, and stronger. And so it's more concentrated. So in terms of a balloon, this is what we might think here. And so this might be a single bond here on the left and a single bond on the right. And there's repulsion, so we can think, the larger the balloon, the bigger the repulsion, so the more space that's needed. And so which one should be a bigger balloon? A single bond or a double bond as far as taking up space? Well, since we have more concentrated, the larger quantity of negative charge density there. And so a double bond is going to require more space than a single bond. It's got twice as many electrons. And then a triple bond is going to have 3 pairs of electrons. And so a triple bond is the strongest of the 3 here and the shortest. And so it's going to have the most concentrated negative charge density there. So requires a lot of space here. How about a lone pair? Sometimes I could stick a lone pair of electrons there. It's not bonded to anything. A lone pair, does it take the same amount of space as a single bond? More space or less space? This is it. If you think about a balloon, this balloon's being pulled by B and A, so it's being stretched or elongated. This balloon here is only being pulled towards one atom. Which atom is it being pulled towards? A. And so here, this balloon is going to be much tighter, much closer to A. There's no other atom pulling on the balloon. And so as far as balloon goes, an A is kind of comparable to a double bond here. A lone pair is comparable to a double bond in terms of balloon size. So here I have 2 equal balloons. That could be like 2 single bonds there. What's the geometry? I don't want to use pair because it's not always a pair. In fact, we talked about, do you remember what a free radical is? What is a free radical? A free radical? Yeah, it has an odd number of electrons, so we aren't even going to have a pair. There's going to be an odd electron stuck there. An odd electron, since it's not a pair, should we consider it a group? Yeah, we got to consider it as a group of electrons too. And so a free radical is going to require space for that electron. There's going to be repulsions there. And so this I don't like to call it electron pair geometry. We'll just call it electron geometry, or electron group geometry, or EG for short, electron geometry. And so when we look at the groups of electrons, geometries, here we could have different sized balloons, but if we have 2 balloons, it's always going to adopt a linear arrangement. You know, one balloon could be bigger or smaller, doesn't matter, but it's going to be linear if we have two groups. If we add a third balloon there, it can't be linear anymore. Third balloon, in order to minimize the repulsion, we're going to adopt this geometry. What was this geometry called again? This electron geometry? Trigonal planar. This is trigonal planar. And even if I have a big balloon, let's replace this one with a big balloon here. If I replace this one with a bigger balloon, it might distort this a little bit, right? But it's still going to be trigonal planar. If I have a fourth balloon, I'll try to put it on top here. So I put a fourth balloon here, it's going to push these 3 down. And this, you know what shape this is called? This electron geometry? Tetrahedral, the 4-sided polygon. And so this tetrahedral shape is very important. Here. This is one we should try to learn how to draw on the board. We're not going to draw using balloons. We'll draw using maybe sticks to represent bonds or something like that. Linear is pretty easy to draw. Trigonal planar is not too bad. Tetrahedral is more difficult. And so we're always going to draw tetrahedral, let's say, the same way. And so let's say put one group straight out like this. So this might be a single bond going up, and then one group coming down like this. Now to maximize the distance between these, do you know what the angle on tetrahedral is? When we go back and take a look at the angle, let me go back here, it's easier to see. In order to maximize the distance between four groups, they should adopt a 109.5 degree angle. So between the top and this right one is 109.5. This right one and the front one is also 109.5. This left one and the front one is 109.5. But what about these two back ones? What's the angle here between the two back ones? The angle here between the two back ones is also 109.5. In fact, all the angles are 109.5. And so, you know what? There's no top, there's no bottom. This is what we call spherical symmetry. There's no top, there's no bottom. You know, all the angles are the same at 109.5. And so this is tetrahedral here. And so what we want to do is we want to draw this. In order to draw this, we want to put as much into the plane of the board as possible. So let's say there are four single bond groups. If I have four single bond groups, then I'm going to align it like this. I put A here, it's the center atom. One group in the plane of the board, one group in the plane of the board coming down, but this group is not going to be in the plane of the board. This group is going to stick out. If this group sticks out, we draw a wedge. Okay, that's fine. And then there's a group behind it that sticks in. The group behind this, we draw a dashed wedge. And so here, all the angles, no matter what angle I'm looking at, you know, no matter what atom you grab, it's always the same. And so all the angles are the same at 109.5, and tetrahedral geometry is still called spherically symmetric. So that's what we're showing. So we can see that here with the groups. Basically, I would draw this balloon in the plane, this balloon in the plane. It's 109.5. This balloon coming out, down and out here, and this balloon going in and down here. And so here, like this. They don't have to be single bonds. They could be anything. It could be a radical. It could be a lone pair. It could be a double bond. And so it's going to look like this. You know, one group here, one group here, one group coming out, one group going in. So my four balloons. Tetrahedral. Okay, those are the three electron geometries that we're going to encounter. Three electron geometries. So this talks about electron pair and something called molecular geometry. Let's take a look at this table. Line 1, 2, 3, 4. That's, I don't know, just what row we're in. This doesn't mean anything. This first column. The second column does. Regions of electron density. Asterisk. What is regions of electron density? You heard that word? Regions of electron density. Now, what does that mean, regions of electron density? Regions of electron density, what this means is number of groups. How many groups of electrons do you have around the atom? You have one group, two groups, three groups? That's regions of electron density. You know, in this case, if we have two groups, ignore this column for right now. What is it? Well, two groups is going to adopt the linear electron geometry. If we have three groups, it's going to adopt the trigonal planar electron geometry. What if we have four groups? If we have four groups, it's going to adopt the tetrahedral electron geometry. All right, so why do we have two trigonal planars here? The reason we have two trigonal planares is because there's another geometry. The electron geometry is not ultimately what we're after. Electron geometry is just a stepping stone to something called the molecular geometry. We're most interested in the molecular geometry. We really don't care about the electron geometry, but we need to figure out the electron geometry to determine the proper molecular geometry. The molecular geometry is based on two things. It's based on the atoms, the bonded atoms. So this is what bonded regions mean, how many bonded atoms we have. Not bonded, well, I guess bonded regions means a single bond, double bond, or triple bond. And the electron geometry. And so here, let's put some atoms here, here, and here. And so we have something like this. This is three groups of electrons, single bond, single bond, single bond. And then when we look at the atoms are arranged in the same fashion as electron groups. And so the molecular geometry is trigonal planar. If the molecular geometry is trigonal planar, it matches with the electron geometry, which is trigonal planar. But it doesn't have to match. Sometimes the molecular geometry does not match the electron geometry, as in this case. In this case, the electron geometry is trigonal planar. And it doesn't matter what the group is. This is a lone pair, this is a double bond, this is a single bond. So we can still have three groups of electrons because we cannot split the lone pair into two separate groups. And we cannot split the double bond into two single bonds. The double bond has to be taken as a whole. And so three groups of electrons. Three groups means electron geometry is trigonal planar. However, when we look at the atoms, we have these three bonded atoms. The three bonded atoms are angular or bent. Here we have three bonded atoms, but the three bonded atoms are linear. The difference between this and this is there's a lone pair here. You've got to accommodate. There's no lone pair here, so this can stay linear. And so this is a linear electron group geometry and a linear molecular geometry. However, we might expect this to be a linear molecular geometry. It's not because the lone pair is going to push these other two groups in, and the ABA angle should be about 120 degrees. Three groups. Anyway, the molecular geometry for this is called angular or bent here. So the same thing happens about this. Now, the situation is this. Why don't we call this trigonal planar 2? We don't call this trigonal planar 2 because can we pinpoint the electrons? Are the electrons here and here? One electron right here and the other electron's right there. No, we don't pinpoint the electrons. We don't pinpoint the electrons because of that principle. What is that principle? And the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle means you can maybe pinpoint it here, but then the next instant it might be over here or over here. And so there's just an electron cloud here. That's it. However, the atoms. Do the atoms jump around like birds? So one time the atom's here, and the next instant the atom's over here, and the next instant the atom's over there. Are the atoms jumping around like the birds, flying in some kind of random fashion? What do you think? No, the atoms kind of stay put. The atoms we can pinpoint. We don't have to worry about the Heisenberg uncertainty principle for atoms. Atoms are what's called massive. There are some of them. There are details I'm not getting into in Heisenberg, but for atoms being massive, they're easy to pinpoint. And so the atoms can be pinpointed. We can see this molecular geometry. However, to pinpoint the electrons here is not easy. So we just call this angular bent. It's easy to see with things like X-rays. Angular bent. Why is it angular bent? It's got to be because of the electron density up here, electron cloud up here, pushing these two in. That's what we get. And so ultimately, we're after the molecular geometry. The molecular geometry is important. That's what we see or observe experimentally. For tetrahedral, we have three molecular geometries that are possible. For tetrahedral, a tetrahedral always has four groups. But if we have four bonded atoms, then the molecular geometry is also tetrahedral. This is an awful tetrahedral structure. Because when I look at the ABA angle looks like what? The ABA angle looks to be 90 degrees. Is it 90? No, it's 109.5. That's an awful drawing. But that's okay because Lewis structures, nobody's saying that I'm going to draw a three-dimensionally accurate Lewis structure. No one does that. The only time you're going to be asked to draw a three-dimensionally accurate structure is when the book says draw a wedge dash diagram. A wedge dash diagram means if it's sticking out, draw a wedge. If it's going in, draw a dash. Wedge dash diagram. Or I might ask for a three-dimensional Lewis structure. If I'm asking for a three-dimensional Lewis structure, I would redraw that thing, because that's giving no indication of the structure, the BA4 molecule. And so the way I draw it is it looks like 4 single bonds to some generic atoms. So we put B in the center. One bond goes up, the other bond goes down. The angle, 109.5. One bond comes out as a wedge, the other comes in as a dash. The angle's 109.5. And so we'll put A here, A here, A here, A here. And so we see we have an electron geometry that's tetrahedral, and we have a molecular geometry which is the same, tetrahedral. So the molecular geometry is tetrahedral. Like electron geometry is tetrahedral. And again, electron geometry is just a stepping stone to molecular geometry. Ultimately, what we want is molecular geometry. Now we can make a prediction about the angle. The ABA angle should be 109.5 degrees. Okay, that's one of the molecular geometries. Another molecular geometry that we see for the tetrahedral electron geometry is this. Well, let's remove one of the bonds and replace it with a lone pair. So again, we still have 4 groups. 3 single bonds and 1 lone pair. If we have 4 groups, then they want to get as far apart from each other as possible. So they'll adopt the tetrahedral. This is an awful tetrahedral as well. That's a really bad tetrahedral. That's a really bad tetrahedral. In fact, they aren't being consistent how they draw. Well, they are here, but for the rest of the book, yeah. Okay, here then, this is pretty bad too, because what is it? This looks like a T to me, a T-shaped molecule. Is it a T-shaped molecule? Like the letter T? No, the capital letter T. No. This is actually called trigonal pyramidal, but it certainly doesn't look trigonal pyramidal. Unless you draw like this. I mean, if you draw like this, it'll look a lot more trigonal pyramidal. That is, we'll put the lone pair here in the plane of the board. And we'll put one of the bonds in the plane. So this lone pair and this bond is in the plane. That means this bond sticks out and this bond goes in. And so what this is like a pyramid, except with a triangular base. So a triangular base pyramid. So what we have is something like this. We'll just take out this. So we got this lone pair still stuck on here. So something like this. That's what I'm trying to draw here. So this one's sticking out, this one's going in, this is in the plane, this is in the plane here. That's trigonal pyramidal. What's the angle? The ABA angle here. The ABA angle should be 109.5 degrees. But you know, the observed angle is a little different. For example, ammonia. Ammonia would adopt this type of structure. What happens is this lone pair being pulled to another atom up here? No. And so if there's no atom up here pulling the lone pair, that balloon's going to collapse down here. As the balloon collapses down here, it's going to push these in because this one has greater repulsions. This one requires more space. And so if it pushes these 3 down, what it does is it shortens the angle here, or tightens the angle. And so what's observed is more like a 107 degree angle rather than a 109 degree angle. So a lot of people will call this 109. When you round 109.5 to 3 decimal, I mean not 3 sig figs, what does it round to? It should round to 110. This 0.5 we round up. But the actual tetrahedral angle is not 109.5. It's 109.47, I think, 46. 109.47. If the angle is 109.47, then we round it to 109.5, right? But we don't do a cascading round step. That is, if it's 109.47, do we round it like this? 109.47 rounds to 109.5. 109.5 rounds to 110. Do we do two round-offs in a row? No. And so a lot of people will call this either 109.5 or 109. To 3 sig figs, it'd be 109 degrees. And so, in fact, I'd say half the people will call this a 109 angle. The other half who want to be more precise will call it 109.5. Well, anyway, this one gets distorted, you know, so it's less than 109.5 because this balloon's bigger. If this balloon's bigger, it takes up more space, pushes these balloons down, and so the distorted angle is about 107 degrees distorted. An example of this would be ammonia. In ammonia, the H and H angle is 107. Ammonia. The H and H angle is 107. We expect it to be 109 undistorted. That's about 107. That's because lone pairs take up more space than single bonds. Okay, there's one more geometry here, and that is if we have two lone pairs and two bonded atoms. If we have two lone pairs and two bonded atoms, then that's four groups, two lone pairs, two bonded atoms. It's going to adopt a tetrahedral electron geometry. But the molecular geometry is going to be different. It's going to be bent or angular, but this bent or angular is different than this one. This is bent at 120, this is bent at 109. Bent at 109 because we have these two lone pairs here. I'm pushing this in. And so if I drew this three-dimensionally, we typically draw like this. Put B here. I'll put the two bonded atoms in the plane. This goes in the plane. So if I put the two bonded atoms in the plane, then one lone pair sticks out like this. This would be the wedge. And then one lone pair is dotted in like this or dashed in. That would be the dash. I draw the lone pairs like this. If the lone pair looks like this, it's in the plane. If the lone pair looks like this, it's a wedge coming out. If the lone pair looks like this, it's a dash going in. And so I have three ways of drawing lone pairs. In plane, out of plane coming out of plane going in. Just like the bonds, you draw them like this. I'll draw the lone pairs like that. But of course Heisenberg plays a role, but you know, Heisenberg is going to give you a probability boundary. Probability of finding these are better out here than there for these ones. Water is the example of this, you know, water. And so the ABA angle, should be 109.5 degrees. But having two lone pairs there will distort it, you know. Each lone pair, because now, rather than spreading out the electron density out here, we pop off this atom, like this. This lone pair is going to collapse in down here, kind of put stress here. Same thing here. Pop off this atom. Now we got two lone pairs. These two lone pairs come in, put stress on these bonding pairs, and pinches it in. And so what we end up with is an angle. The angle should be 109.5, but because of the two lone pairs, it's going to be compressed. And for example, in water, you know what the angle is in water? So HOH. The HOH angle here is 105 degrees. And so it looks as if the each lone pair distorts the angle by 2 degrees. That's what it looks like. Okay, what did we call this molecular geometry here? Yeah, pyramidal, but not a square pyramid like the pyramids of Egypt. The pyramids of Egypt are square pyramids because they have a square base. This has a triangular base, so we call it not square pyramidal, we call it trigonal. Trigonal pyramidal. Electron geometry is the same. All of these electron geometry, tetrahedral, 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 but the molecular geometries are different. So the molecular geometry here, what is this called? Bent. This is bent at 109. We have two bents. You know, the other bent that we saw is up here. This is bent at 120. This could be distorted as well. We'll talk about the distortions. The footnotes: a region of electron density is a single bond, double bond, triple bond, lone pair, or single electron. Those are radicals. All bond angles are ideal. There could be distortions to the bond angles. So here we see the three molecular geometry for tetrahedral electron geometry. 4 bonded atoms, 3 bonded atoms, 1 lone pair, 2 bonded atoms, 2 lone pairs. Water. How to draw. We don't need instructions for drawing these. Let's just get some practice. Let's do NCl3. Nitrogen trichloride. We'll draw the wedge and dash diagram for nitrogen trichloride, NCl3. Different ways of doing Lewis structures. We can follow the steps in doing Lewis structures, or we can just look at what we got. We have nitrogen. Nitrogen has 5 valence electrons, and then we have chlorine. Chlorine has 7 valence electrons. Nitrogen wants 3 more electrons, chlorine just wants 1. Is chlorine strong enough to take it away from nitrogen? Can chlorine strip the electron off nitrogen? What do you think? Well, you can take a look at the, where's that chart? Oh, the strength. If you look at nitrogen, nitrogen is 3L, chlorine is a 3,2. Will chlorine strip the electrons off nitrogen? No. They're pretty comparable in strength. And so what's going to happen is we're going to form a covalent or an ionic bond. We're going to form a covalent bond here. So we got to share it. And so what's going to happen is you see this electron here and this electron here, they end up sharing. Because nitrogen wants 1, chlorine wants 1, they're going to end up sharing electrons. So, like this. Then we'll have another one here, another one here. We got some lone pairs, so we can fill it out like that. And so here we could just skip the steps and put the pieces together. This is a little different. Nitrogen trichloride. This is perfectly fine for nitrogen trichloride, the Lewis structure. The Lewis structure does not have to indicate the 3D structure again. But a lot of people sometimes they get mixed up thinking it should, because what do you think the CL-NCL angle is? The CL-NCL angle. It looks like it's 90 degrees, but it's not. It's not 90 degrees. It's not 120 either. What is it? It's 109.5. It's 109.5 because it's a tetrahedral electron geometry. This is why we need to know the electron geometry before we figure out the molecular geometry. Electron geometry is tetrahedral. Well, what is the molecular geometry of this? Is molecular geometry tetrahedral too? No. So let's go ahead and figure out the position. For tetrahedral, we do two in the plane, one coming out, one going in. So one of the ones I'll put in the plane is the lone pair. This is a lone pair in the plane. And then I'll put one of the chlorines in the plane. So we have a chlorine here, like this, in the plane. That means one chlorine comes out of the plane, which is the wedge, and one chlorine goes into the plane, which is the dash. So this is kind of the 3D Lewis structure for this. And so the electron geometry is tetrahedral, but what is the molecular geometry for this? Yeah, the molecular geometry is trigonal trigonal pyramidal. Trigonal pyramidal molecular geometry. And that's based on an electron geometry tetrahedral. All right, so we want to kind of predict the CL-NCL angle. What is the ideal angle here? 109.5. What do you think? Is it going to be distorted? Yes, it's going to be distorted because there's a big balloon there. The big balloon is the lone pair. It's going to compress the other three chlorines down, and it does what? Yeah. Chlorine's a bigger atom, but we don't factor that in. We should factor in, but it's too much. We just treat this as a single bond. That's more important than a lone pair. So it's going to shrink the angle. So we would expect maybe about 107 distorted. About 2 degrees per lone pair. We only got one lone pair, so 1 degree. 2 degrees distortion. I don't like this one. I like the Brooks diagram a lot. Two things I really dislike about the Brooks diagram here. One, the book shows no lone pairs. You're only allowed to do that once you hit organic chemistry. Once you hit organic chemistry, then you can forego the lone pairs, because you should be able to look at it and then just imagine what the lone pairs are. So when I look at that, I know the lone pairs. But even if you're in organic chemistry, you still don't want to forget the lone pairs, because the lone pairs are important for other reasons as well. And so I just don't like that they don't include the lone pairs. If you decide not to include the lone pairs, that's a pretty big deduction of the Lewis structure. The other thing I don't like is the perspective that they're looking at this. When I try to match their perspective here, I'd have to look at it like this, kind of, because what I'm saying is, oh, there should be a lone pair. Here. I'm kind of looking at it like this because I have one chlorine in the plane, one chlorine coming out and above, and then one chlorine going in and below, right? But normally when I look at this, I look from above. I look from above. When you look from above, then one chlorine comes out and the other chlorine is above it going in. And so I don't like this. I would put the wedge behind and above the other chlorine by looking at it from this perspective. You can see it here. But try to get it in there. No, you know, mine is flipped here. Mine's flipped because the angle I'm looking at it is different. So anyway, the wedge and dash diagram reflects tetrahedral electron pair geometry with one lone pair of electrons. This whole thing about multiple bonds, we don't need to get into all this stuff. This is way too much stuff about it here. With multiple bonds, it's just the same thing. You just treat a multiple bond as a group electron. So we could take a look. We're not going to do C2F4 first. Let's do something easier. For multiple bonds. Something easier would be like CO2. CO2, there are different ways we can do CO2. One, we can just use Lewis symbols and put it together. Another is we can follow the instructions. If we follow the instructions, then, you know, carbon has 4 electrons, oxygen has 6 valence electrons. These are valence. This altogether is 16 electrons. And then what we do is we put the atoms, like for example this, COO. Is that a good base structure there? No. What did I say about OO bonds? OO, this bond here, OO single bonds. What did I say about those? You've seen them before. Like for example, hydrogen peroxide. What did I say about that? An OO single bond is called a peroxide bond. What do you know about peroxide? Are peroxides stable or unstable? They're unstable. That's what you should know about peroxides. They're unstable. Why are they unstable? They're unstable because of the O single bond. Why, or what about O single bonds causes it? Well, that's getting too deep, but basically it's because of the size of the atoms and the proximity. We'll talk a little bit more about it, but in Chem 1A, get into it heavily. But basically, OO single bonds are something to avoid. This is why one of the rules comes up. If we're going to stick an atom in the center, we'd like to stick the least electronegative atom. So carbon would be it. And then we'll attach 2 oxygens to that. Okay, what's the next step? After we come up with a skeleton, well, single bonds, we do what? So far, we've used up four of our 16 electrons. We got 12 electrons left over. We complete the octet to the center or to the outsides? To the outsides first, the terminal atoms first. So we complete the octets to the terminal. Octet means 8, and so we'll put 3 lone pairs. If we have 3 lone pairs in one bond, that's 8 electrons, which is an octet. 3 lone pairs in one bond, 8 electrons, that's an octet. How many electrons have we used so far? All of them. All 16 electrons. We're done. But the structure doesn't look good. What's wrong with this structure? The carbon. The carbon's very unhappy. Why? Yeah, the carbon doesn't even have anything close to an octet. The carbon only has 4 electrons around it. It's short of an octet. So we can use a trick to make it an octet, and that is form multiple bonds. If we form multiple bonds, we can do it. So we don't add any electrons, we don't remove any electrons, we just reposition the electrons. So let's take this pair of electrons and drop it in here. Okay, and we'll do the same thing over here. And so if we form a double bond on the left and a double bond on the right, carbon will be happy. Carbon will be happy because now it has an octet. But that's not the only way to make an octet. You know, what we could have done instead was we could have taken two pairs off one oxygen. And so an alternate way is, let's leave this oxygen alone, and then we'll take one lone pair, bring it into the bond, and we'll take the second lone pair and bring it into the bond. And so we're only left with one lone pair on this oxygen. The two lone pairs were used to make a triple bond. Single bonds are longer, but I'm running out of room here. How about this structure? How does this look to you? Now, this, I see, does this oxygen have an octet? Yeah. Does carbon have an octet? Yeah. Does oxygen have an octet? Yeah. Is octet the only thing we look at? No, what else do we look at when we're looking at structures? The charge. Okay, so we always look at the charge. I do. I always look at the charge. What is the charge on this oxygen, the formal charge? It's 6. It's supposed to have 6. It's 6, and it has supposed to have 6, then it's even. 0. Carbon? 4. It's supposed to have 4. That's good. This oxygen is 6. It's supposed to have 6. It's good. The formal charge is all 0 here. The formal charges of 0 are good because what they put into the structure is what they got out. Carbon put in 4, got out 4. Oxygen put in 6, got out 6. How about the formal charges over here? What's the formal charge on this oxygen? Well, this one has 5, but it put in 6. If it puts in 6 and it only gets 5 back, then it's short 1 electron. If it's short 1 electron, we call it positive or negative? Positive. Short 1 electron. This one is how many? This one's 2, 4, 6, 7. You know, because we split these 50-50. So 2, 4, 6, 7. This one ends up with 7 electrons. How many did it put in? 6. So it put in 6, it got 7. If it put in 6, got 7, it came out with an extra electron. If it comes out with an extra electron, is it positive or negative? An extra electron makes it negative. Do you like this structure here? What do you think about this structure? I think this structure looks very bad. Why? This structure looks very bad to me. Yeah, the formal charges. 1, there's formal charges. This one has no formal charges. 2, if there's a tug of war for an electron, is this oxygen going to pull an electron off this oxygen? So the right oxygen is stronger than the left oxygen, so it pulls an electron. No. This is an impossible situation. 1 oxygen, you know, this is terribly unstable here. And so we would automatically eliminate this structure because it looks so bad. You know, even though everything has an octet, it doesn't look good from the standpoint of 1 oxygen gaining, the other oxygen losing. In an oxygen versus oxygen tug of war, it should come out as a tie. That's oversimplifying things because there could be other issues there. Anyway, here we have 2 double bonds. And so how many groups of electrons are around carbon? Do we have 4 groups? That is, we split the double bond here into 2 single bonds and split this into 2 single bonds. No. This is 2 groups of electrons. 2 groups of electrons will adopt what electron geometry? If I have two groups of electrons, how do I want to position those groups? Do I want to position them in a 109 angle, a 120 angle, or a 180 angle? 180. And so this is going to be 180. The OCO angle is 180. The geometry here, the electron geometry is linear, and the molecular geometry is linear. And this would be the 3D drawing because it's just flat in the plane here. So this is CO2. We handle double bonds the same as we handle any other group of electrons. Now, the example that this slide is going through is C2F4. With C2F4, we're dealing with fluorine. And one of the things with fluorine that I mentioned before is fluorine only forms single bonds. That's a rule. Fluorine forms only one bond. Like hydrogen. This is kind of a rule. Although, you know, when you get into fancy quantum mechanics and bonding like that, then we look at bonding a little differently. But we aren't getting there yet. So we'll just keep it simple. So, you know, where does the rule come from? In other words, why does fluorine only form one bond? Yeah, you can memorize the rule, but what's the basis for the rule? Basis comes like this. You know, over here carbon didn't have an octet, so what did we do? We formed multiple bonds. Because we ran out of electrons, we can't just throw some electrons on carbon. If I draw the Lewis structure BF3, you know, if I have BF3, I'd love to form multiple bonds here. I just need one double bond. Because if I look at that structure, BF3 here, I look at boron. Boron is just 2 electrons short of an octet. And so if I could just form one double bond, done. I don't have to add electrons. I don't have to remove electrons. I just reposition these electrons from here to here. Everybody's happy, right? And so let's do that. I'll take these electrons here and bring them into the bond. Did that destroy the octet on fluorine? No, fluorine still has an octet. Now boron's much happier. Like that. And so we can form multiple bonds like this. One to help complete the octets. That's one way. Or two, you know, because we have excess electrons. So we got to do that. And so looking at this, both structures have octets. But one structure looks great for boron. This looks great for boron, but it's bad for fluorine. Why is it bad for fluorine? Fluorine still has an octet. Why is it bad for fluorine? Yeah, that's the same reason. Because of the charge. What are the formal charges here? What's the formal charge? How many electrons does fluorine have? When we're counting formal charge, we divide these in half. So fluorine has 7. How many is it supposed to have? 7. 0. Boron? how many does it have? 3. How many is it supposed to have? 0. All the formal charges are 0. Okay, how about here? What's the formal charge on this fluorine? This has 6. It's supposed to have 7. It's 1 short. So in other words, fluorine donated some of its electron density to who? Well, to boron. What's boron's? Boron has now 4. It's supposed to have 3, so it came out ahead. So essentially, fluorine gave boron an electron, or boron took an electron from fluorine. Well, I don't think fluorine's going to give any electrons away, so boron would have to take the electron from fluorine. Is boron strong enough to take an electron from fluorine? No. I mean, when you look at the this chart here, you'd see that. We'd see that there's no way that boron at a 2.0 can take an electron from fluorine at a 4.0. In fact, a 2O40, what is delta En? Delta En is 2, which means that this is borderline ionic. This is a borderline ionic bond. In fact, fluorine is going to completely strip boron of its electrons. And so this is borderline ionic. Well, let's just call it on the edge of covalent here, but this is not going to happen. And therefore, in order for fluorine to form a multiple bond, it has to be a very generous donor, but fluorine is not. Fluorine is a taker, it's not a donor. Fluorine is going to take electrons, it doesn't give them. So anyway, this is, so we're stuck here. And in fact, for CO2, we came up with a nice way to make everybody happy. But for BF3, we can't. BF3, it's impossible to make everybody happy here. And so BF3 is kind of an unhappy molecule. Turns out chemically, BF3 is very reactive. BF3 turns out to be what we call a very powerful Lewis acid. Lewis acids are electron pair acceptors. Boron really wants an electron pair from somebody, so it's going to take it from somebody else. If it can't take it from fluorine, it'll find somebody else to take it from. And so that's the reactivity of that. You don't need to know that.
Question, Professor. If the chemical formulas and equations are linear, and it appears that they're supposed to be three-dimensional, is that like thinking outside the box?
No. Linear? I mean planar?
Linear, when I say linear, I mean it's like one plane when you write the equations. And
No, we just write it planar like this to make life easier. It doesn't have to be plane, in the plane. We could stick it out of the plane.
No, what I mean, like, for instance, C2F4, right?
Mm-hmm.
The way it's written there versus the picture, three-dimensional picture of it.
When we do the Lewis structures, we do it with total disregard for the three-dimensional structure. We don't care what the three-dimensional structure looks like. We have no expectations about the three-dimensional. The three-dimensional structure comes after we get the correct Lewis structure. So the first thing is to get the correct Lewis structure for C2F4. You know, and so let's go ahead and figure that out. Carbon, we have 2 of them, 4. Fluorines, we've got 7 electrons for each. I have no idea what the 3D structure of this will look like.
Well, isn't that like 3D, those things right there? The structure, isn't that kind of like 3D?
Yeah, this is 3D. There are 2 ways of drawing this. You know, we can rotate this 90 degrees. If we rotate this 90 degrees, then we get a wedge. That.
So that's 3D.
It's 3D, yeah.
And that's not 3D.
We haven't even drawn the structure yet.
I mean, a C2F4, that's not 3D. That's 3D, but that's not 3D, right?
C2F4, we have to draw the structure out first.
I mean, the way it's written now, C2F4, the letter C and the letter F, that's the way it's written, that's not three-dimensional, is it? Or is it?
It's not three-dimensional. The formula?
Yeah.
The formula is not three-dimensional. No formulas are three-dimensional. Even if I look at the formula for methane, CH4, is that 3D? No. Or methanol, CH3OH. 3D? No. Or methanoic acid, HCOOH. So none of these are 3D. What we do, though, is we try to draw out the Lewis structure. When we draw out the Lewis structure, after we draw out the Lewis structure, then we try to visualize it in 3 dimensions. And that means having to tweak the Lewis structure a little bit. And so when we do the Lewis structure, we don't do it with regard to. And so here I have 2 carbons. Is a carbon-carbon link okay? Can I put 2 carbons together like that? Yeah. Since I have 4 fluorines, what I'll do is maybe I'll put 2 on this carbon and 2 on this carbon. Make it even. What do you think about this structure? Does that look okay? Yeah. Can you think of another way of arranging the atoms? Okay, remember, we don't care how I write this.
Oh.
Doesn't matter. I'm going to tweak everything once the structure is written. And so whether you write it down or up, I don't care. Later on, we'll see what the structure is. Because right now, it looks like the FCC angle is 180, and the FCF angle is 90. Okay. But I can easily tweak that around. For example, now it looks like the FCF angle is 45. Okay. Less than 45, 35. It doesn't matter. And so don't worry about the angles when you coming up with the Lewis structure. Okay, then what? Are we going to do the, yeah, let's do the same thing. We'll just keep going. We'll end early today. Then what? Well, how many electrons do we have?
36 total.
36 electrons? So how many have we used? 10? And so we have a lot of extra electrons. What should we do with the extra electrons? Yeah. So go ahead and do that. Fluorine really wants an octet, much more so than carbon. So once we finish the octet on the outside, then how many electrons have we used now? Oh, we have 2 more electrons? Yeah, so we use 34 electrons. So we have 2 more electrons. We can't put these on. These already got an octet, but carbon doesn't. And so maybe if we have 2 more electrons, we'll put 1 here and 1 here, something like that. Be fair to each carbon. But we still have a problem now. What's the problem? Octet around carbon. But this is an easy fix. How can we fix it? Just make a double bond here. So it's going to look like this. And let's throw in the fluorines in here. All right, so this is the structure. We've used all 36 electrons here. Okay, in this particular structure, what we have is we have something called two central atoms. Now, with two central atoms, the situation is we do one at a time to figure out the electron geometry and the molecular geometry. And so normally what we do is we label it. Like, for example, this would be called carbon 1. And then this one would be called carbon 2. Just some arbitrary label for right now. And so what we do is we first look at carbon 1, and then we look at the electron geometry and figure out the molecular geometry. So if we look at carbon 1 here, what is the electron geometry? Well, to figure out the electron geometry, we're either going to have 2, 3, or 4 groups. How many groups of electrons are on this carbon? 2, 3, or 4? Three or 4? I think it's 3. 3. 3 is correct. Single bond, 1. Single bond, 2. Double bond, 3. 3 groups of electrons. If it's 3 groups of electrons, what geometry does it adopt? Linear, trigonal planar, or tetrahedral? Trigonal planar. And so this is trigonal planar, which sets the angles at 120. Now we look at the atoms. The bonded atoms, we have a fluorine, and a carbon. When we look at the bonded atoms are in the same trigonal planar shape. And so the molecular geometry around carbon 1 is trigonal planar. That's the molecular geometry. The electron geometry is also trigonal planar, which we figured out first. With trigonal planar, then the angle should be at 120. But let's take a look at the angles. The FCF angle. The FCF angle. Do we have 3 equal sized balloons, or no, we don't? And so in this case, this one's going to be bigger. This one, double bond's bigger, so it's going to push these 2 single bonds in. And so the FCF angle is normally 120 degrees, but we expect a distortion. The distortion is this is going to push it in by about 2 degrees. But it's tricky because what happens is the FCC angle, if we look at the FCC angle, that expands by 2 degrees. So if we've got a bigger balloon here, this expands it. And so the FCC angle is normally 120 degrees, but because this is a double bond, we expect it to be about 122 degrees distorted. Well, that goes the same here on this side. So if this is pushed out 2 degrees and this is pushed out 2 degrees, then this is going to be pushed in by 4 degrees. And so this one is about 116 degrees. Again, these are just rough approximations. These are not accurate, but we're just trying to get a gauge of what the distortions are. And so this one's expanded, this one's contracted. And so molecular geometry, trigonal planar, the electron geometry is trigonal planar as well. What about this carbon here? Carbon's the same. These are mirror images of each, so it's the same. In fact, this molecule's flat, like a pancake. It's flat. So we don't have to draw wedges and dashes. What we can do is we can just lay it flat on the plane of the paper or the plane of the board. We can also rotate this. Then we'd have to draw wedges and dashes, but we aren't. We're just going to leave it flat on the plane. And so this is the 3D structure here. The angles are about 120, all of them. And this is trigonal planar. This carbon over here is also trigonal planar. Both of them are trigonal planar. That would be the 3E drawing for this. Again, they don't put the lone pairs there. I like to put the lone pairs there. So get in the habit of putting lone pairs in. Okay, once we know the geometry, we can predict one thing, or we can determine one thing, and that is the polarity. Polarity, remember poles, we have a positive pole and a negative pole. Polarity, or molecule polarity, or molecule dipoles, as we call them, are important. They're important in solubilities. So for example, light dissolves light. And so let's take a look at some examples of polarity determined from the 3D shape. Carbon versus chlorine. When I look at a carbon-chlorine, you know, chlorine's more electronegative. What kind of bond is this? Is this an ionic bond? This is carbon, this is chlorine. Ionic bond, polar covalent bond, or non-polar covalent bond? Depends on the electronegativity difference between carbon and chlorine. What would your guess be? So chlorine's a 3,2, carbon is a 2,6. So is that a negligible difference in strength? If it's a negligible difference in strength, then we call it nonpolar. You know, they're both kind of the same strength. It's going to be a tie. Is it a huge difference in strength? If it's a huge difference in strength, we call it ionic. You know, chlorine will strip the electron off carbon completely, form ions. Or is it a moderate difference in strength? If it's a moderate difference in strength, we call it polar covalent. So what is it? Polar covalent. It's a polar covalent bond. It's a moderate difference. Well, let's go back to the structure here. Well, anyway, it's a polar bond. So a polar bond will have a negative end and a positive end. What's this symbol called here? This symbol is a Greek symbol, Greek letter, lowercase Greek letter, delta. What does delta mean? Partial, it means partial. And so this is a partial negative charge. It's not a full negative charge because chlorine's not powerful enough to strip the electron completely away from carbon. But it can suck the electron cloud towards it, making this end more negative. So this is partial negative, this is partial positive. If it can completely strip it, it'd be a full negative charge, and we just call it negative. Carbon would end up positive. Instead, it's a partial because it's what we call a polar covalent bond. And so, in other words, we have what we call a bond dipole, or a polar bond. We have a bond dipole like this. In fact, we have 4 carbon-chlorine bonds. This is carbon tetrachloride. The 4 carbon-chlorine bonds, all these have a bond dipole, delta plus, delta minus, delta plus, delta minus, delta plus, delta minus. However, this molecule is nonpolar. How can we have polar bonds and the molecule be nonpolar? Well, probably the easiest way to see that is like this. Take a look at this molecule here. Does this molecule have polar bonds? Yeah, fluorine, carbon. This is the polar bond here. Fluorine is more powerful than carbon. So, you know, when I look at this electron cloud, this balloon is tweaked in shape. This balloon is going to be like this. Why? Because fluorine's going to be sucking all the air in the balloon towards it, right? It's stronger. And so that's going to result in a delta minus here and a delta plus here. This is what we call a polar bond. It's not ionic because fluorine is not strong enough to completely strip carbon, because carbon's a 2.6, fluorine's a 4.0. not strong enough. All right, this is a polar bond here too. This is delta minus, this is delta plus. This is a polar bond here, delta minus. This is delta plus, delta minus, delta plus. And so we got polar bonds here. What about carbon versus carbon? Is that a polar bond or not? That's a non-polar bond. No difference in strength there. Non-polar bond. And so the electron cloud has not been polarized. So when we look at this, this has a whole bunch of polar bonds, and yet this is what we call non-polar. What difference does it make if it's polar or non-polar? The difference it makes is something like this. C2F2 will dissolve in oil, or will it dissolve in water? Will it dissolve in oil, or will it dissolve in water? C2F2 will dissolve in oil, but it will not dissolve in water. Why? Like dissolves like. And so this is non-polar. But why is this non-polar? It's got 4 polar bonds, and yet it's non-polar. Because we're looking at molecular polarity. In other words, we're looking for a molecular dipole. A dipole is a positive end and a negative end. When we look for a molecular dipole, the molecular dipole is equal to the sum over 3 dimensions of the bond dipoles. And so we got to imagine the bond dipoles like this. And if we sum these up, we're looking for net movement. And so we got 2 fluorines pulling, one up here, one down here. We got 2 fluorines pulling this way. But do you see the 4 fluorines are pulling in equal and opposite directions? If the 4 fluorines are pulling in equal and opposite directions, there's no net movement. And if there's no net movement, we call it non-polar. In other words, the bond dipoles cancel each other out. This is non-polar. Here, this is what we call spherical symmetry. Tetrahedron spherical symmetry. If you're inside a sphere, this is kind of the structure you'd adopt to stabilize things. These are all equal and opposite here, and therefore it's non-polar. However, if we replace one of the chlorines with a hydrogen, what's the electronegativity difference between carbon and hydrogen? The electronegativity difference between carbon and hydrogen is negligible. It's 0.4. 0.4 is nothing. And so we really don't put a delta plus there. This is kind of non-polar here. And so now we have these 3 chlorines pulling. We have 3 chlorines pulling this way, but there's nothing pulling it back this way. And so there's going to be net movement. The net movement is this way. And so this is what this arrow is showing, the net movement. This arrow is showing the molecular dipole. The molecular dipole points to the negative end. This is called the positive tail. We can have molecular dipoles. We can also have bond dipoles. Bond dipoles would be like this here. The arrow would point to the negative end. The positive tail would be here. So this would be the bond dipole. And so when we sum up the bond dipoles over here, this is the way we did look at it. If you had vector algebra, then we're just adding vectors. When we add vectors like this, we look at the x and the y components, they cancel each other out with vector algebra. Or if you just think, if we had a tug-of-war, there's no net movement. Equal and opposite. The same thing here. In tetrahedral it's hard to see, but this is spherical symmetry, so everything's equal and opposite. Here we don't have it anymore, and so there's going to be net movement. The net movement will be out towards these 3 chlorine. What if we replace another chlorine with a hydrogen? So we have 2 hydrogens here, 2 chlorines here. Well, the carbon hydrogen, this is non-polar, non-polar. And so the net movement will be this way. We have a bond dipole pulling this way, a bond dipole pulling this way, so both of those acting in unison will pull it this way. You see the net movement's going to go this way? And the molecular dipole shown here is going this way. Let's take a look at the molecular dipole. The molecular dipole is the sum of the bond dipoles. So when we look at the molecular dipole, which they call the net dipole being the sum of the bond dipoles, one bond dipole here, one bond dipole here, net dipole this way. Let's remove 3 chlorines and replace those with 3 hydrogens here. So these are carbon-hydrogen bonds. The electronegativity difference is too small. It's negligible. And so this is non-polar here. All hydrocarbons are non-polar. And so all we're looking at here is this way. So the net, the bond dipole is pulling up this way. nothing to cancel out, so the molecular dipole and bond dipole are the same. Here. What if we replace all of them with hydrogen? If we replace all of them with hydrogen, we don't think in terms of this here. If we replace all of them with hydrogen, we think of carbon-hydrogen bond as being non-polar. And so even if I replace this with a carbon, there's no net movement anywhere. And so they should draw so small, they're negligible. The bond dipoles are so small, they're negligible. And so even if this is asymmetric and things don't cancel out, it still cancels out. It's still non-polar. And so no matter how funny the shape of a hydrocarbon is, all hydrocarbons are non-polar. All hydrocarbons are non-polar. And so I don't like putting double pluses and double minuses on hydrocarbons, like your book does. How about CO2? CO2 has bond dipoles here. CO2 has a bond dipole here and a bond dipole here. Will it have a net dipole or a molecular dipole? So this oxygen's pulling electron cloud this way, this oxygen's pulling in the opposite way. Will they cancel each other out, or will there be net movement? In other words, will the carbon move to the left, or will the carbon move to the right, or the carbon's just going to stay put? Stay put. Okay, over here, this oxygen's pulling on this hydrogen this way, and it's pulling on this hydrogen this way. Is it going to stay put, or is there net movement? There's going to be net movement. If this one's pulling this way, this one's pulling this way, it's going to the net movement's going to be up. And so this is going to be the the molecular dipole or the net dipole. It's going to be up. So we add these two together, it's going to move up. And so water is very polar. Is CO2 polar? Does CO2 dissolve in water or bubble out of water? It bubbles out of water. Okay, I'm going to talk about organic chemistry next time, but I want to just do a quick check here. This quiz, this is another little one-pointer, but this will be what we'll end with here today. On this quiz, can you work open notes, but it's going to be individual. That is just there should be some extras back there. All right, can you just do this individual? And what I want you to do is I want you to write the Lewis structure for this. Normally on the test, I would not give you the formula. On the test, I just give you the name and expect you to write out the formula. And so on the exam, it would be like this. Draw the Lewis structure for bicarbonate. On this one, I'll just tell you bicarbonate HCO3 minus. And so just draw the Lewis structure. Be as detailed as you can. I'll throw in some bonus there. So bonus 1, draw the resonance forms. Resonance forms or structures. For resonance forms of structures, I want you to connect those with the double-headed arrow. Remember the double-headed arrows used so you draw one resonance form here, connect it to another resonance form here with the double-headed arrow. And I know those are resonance forms. I'll throw in one more bonus here. One more bonus would be bonus 2. Draw the hybrid structure. This is often called the resonance hybrid structure. So just draw the Lewis structure as detailed as possible, and then the